Okay, hi everyone. Welcome to the exercise class. So today is the first exercise class when we shift from our discussion on thermodynamics and clocks to peculiar features of quantum theory, namely some settings where our classical intuition does not really work. So we would expect one outcome out of our classical experience, but quantum theory actually gives us something else, which we don't expect. And so here we will look at the quantum pigeonhole principle, which I'll explain in a bit. And so first we'll look at like what this means classically and which intuition we would have about this classically. And then we'll see that actually in quantum settings for a particular scenario, this our prediction is not actually correct. Okay, so what is a pigeonhole principle? So suppose that you have 3 pigeons and 2 boxes. And then I just want to take these pigeons and somehow squeeze them into these 2 boxes. Then I can make a following statement that at least 2 pigeons, so if I start squeezing my pigeons in the boxes, in hindsight, I think I should have made the boxes bigger, but they'll have to fit in somehow. So then at least 2 of the pigeons will end up in the same box. So classical. And this is quite obvious from the classical point of view because like suppose that there does not exist such a box, then each box contains at most 1 pigeon, then the number of pigeons has to be at most 2, and we have 3. This is one of the examples of a broader principle which is also known as Dirichlet principle. However, we will now see that if we substitute our pigeons with quantum particles and then also ask ourselves whether these 2 particles are in the same box or not, then we will see that actually we can have a situation where we would have 3 particles, 2 boxes, but none of these 2 particles will be found in the same box. Okay, so the idea of the exercise is that in quantum mechanics, there are settings where this is not true. And considering the settings will also give us some insight about the nature of quantum correlations compared to classical correlations. So let us start with the setting that we'll consider. So essentially what we will have is again like these 2 boxes, which we label as L and R, so left box and the right box. And we have 3 particles, which we label as 1, 2, and 3, which emulate the pigeons. And so the total Hilbert space of these 3 particles is the tensor product of their individual Hilbert spaces, which we label as H1, H2, H2, and H3. And each of these particles has 2 degrees of freedom, which is they're either in a box L or they are in a box R. So, and we label these degrees of freedom, the states, as L and R. So for example, the first Hilbert space is the span, like it has the following basis, so L1 and R1. The same for the spaces H2 and H3. And suppose that now we're looking at the particles which we initially prepare as in a superposition of being in the left and in the right box. So prepare the particles 1, 2, and 3. Each one of them we prepare in the state which we label as plus, which is a superposition of the particle being in the left box and the particle being in the right box. And yeah, so here we just insert the label. Okay. And so here with this state just basically means that if we measure that one particle individually, we'll get that with probability 1/2 it is in the left box, and with probability 1/2 it is in the right box. And then the joint state of all three particles, which we label as phi, can be written as plus on the first particle, plus on the second particle, and plus on the third particle. What can we say about this state? Well, if we prepare all these particles in this state, then actually we will now show that any two particles have a non-zero probability to be found in the same box. So we'll show this in a moment. So what does it mean to for the particles to be found in the same box? It means that the state of these two particles has to live in a subspace which is spanned by the vectors corresponding to the both particles either being in the left box or the particles being in the right box. So here we will consider the case only for the first and the second particle, but because you can see that the state in which we prepare the three particles is symmetric with respect to the permutation between particles, you can essentially, that means that whatever statement we make for the particles 1 and 2 can be made for the particles 2 and 3 and 1 and 3. So we'll just so without the loss of generality, we will just consider the case for the first and the second particle. So if they're in the same box, their state has to live in the span in the subspace which is spanned by these two vectors. Sorry for the plus. If so, this is the same box, and if we want to express that they are found in two different boxes, they have to live in a subspace which is spanned by two vectors, which are now the first particle is in the left box, the second particle is in the right box, and the first particle is in the right box, and the second particle is in the left box. So these are different boxes. Then essentially, finding two particles in the same box corresponds to the following projector, which is the sum of projectors for finding them both in a left box and finding them both in a right box, which we label as this. And these are essentially derived from these two vectors LL and RR. And similarly, we can write the projector corresponding to the to us finding these two particles in a different boxes. So there's going to be a sum of projectors corresponding to finding them in a left and right box and a right and left box, respectively, which is going to correspond to the following. Okay, and so then to find the probability of finding two particles in the same box, we would just need to take the trace with respect to this projector. So the probability of finding the particles 1 and 2 in the same box would be trace the projector and the state in which we prepared these particles. So let us do this calculation quickly. So before we start the calculation, what is this projector? So that is already LL plus RR on a first and a second particle. And in the matrix form, these are, this is this matrix, when we only have two diagonal terms corresponding to these entries. Okay, and
sorry, is there?
yes.
I mean, are the pigeons identical? So to say, like, is there?
Yes, we assume that they're identical.
LR and RL, so to say.
So that's exact. So in the original Dirichlet principle, like this pigeonhole principle, all three pigeons, of course, are considered identical. And this is exactly why we model kind of the state in which we prepare our particles, which are pigeons, all in the same state. So each particle is prepared in the state plus.
Mm-hmm.
Does this answer your question?
No, my question is more like, can we distinguish between LR and RL, like at the bottom of this page? Because you have like two different projectors.
You mean between two boxes?
Yeah, so you have like one pigeon in the left box and the other in the right box, but can you distinguish where you have the other pigeon in the left box and the one pigeon in the right box?
Well, I mean, you see that both of the states, like both of these projectors, like for this finding the pigeons in the same box and in a different box, are invariant under the permutation between the boxes L and R, right?
Yeah, no, that should define it. But if you take just one of the projectors, it wouldn't make much.
Yes, I mean this is actually one of the important differences, as in like the question, and we'll touch this difference a bit in the end when we'll consider the consequences of our consideration. But yes, I mean these are two different questions. So you can ask a question which is, oh, are the pigeons in the same box or are they in different boxes?
Mm-hmm.
And it's while asking this question, you actually don't distinguish these two boxes. Like you don't care which one is left and which one is right. However, you can ask another question, which is, oh, is the particle 1 in the left box? And this is a different question.
Yeah. Okay.
Okay. So in a sense, yeah, maybe I'm jumping a bit ahead, but so the question of whether the pigeons are in the same box or a different box or different boxes reveals the correlations between pigeons. But the question about whether whether the pigeon is in the left box or the right box reveals something about the pigeon directly. And yeah, there is a particular trade-off between these questions when you come to the quantum theory. But in any case, so here we just want to, for now, to consider the probability of two pigeons, 1 and 2, being in the same box. Okay, so so we can write this projector in a matrix form like this, and we can also write so our state, like the density matrix of each state, which we will need as, so what is this, plus, so this is just L plus R, L plus R. This is gonna be 1/2 of this matrix. So here I assume that L corresponds to this vector and R corresponds to this vector. So L is usually what we call 0, and then R is usually what we call 1 if we're talking about qubits. Okay, and then now we can calculate the probability by just multiplying several matrices and taking trace. So first we have our projector. And then you can see that because our projector is only acting on the particles 1 and 2, we can actually just throw away the state of the particle 3 because it lives in a tensor product, so we can take it out, and it's in any case a density matrix which has a trace 1. So we can only consider the particles 1 and 2 here. So here we have a tensor product of the density matrix of the particle 1 and the particle 2. Okay, so one step left. Just have to write down the tensor product. I'll bring out the 1/4. And here we'll just have all ones. And essentially we see that we only have to compute the diagonal elements of the matrix, and we only have two diagonal terms which are non-zero, which are these two. So what we get is 2/4, 1/2. So essentially what we just calculated is that the probability of finding the pigeons 1 and 2, the particles 1 and 2 in the same box, is 1/2. Which immediately means that the probability of finding them in different boxes is also 1/2. Okay. For now, there is no immediate validation of anything. We're just calculating probabilities. However, now the plot will start to thicken because we want to show that there are some instances in which we can guarantee that no two particles are in the same box. For this, to show this, we will just subject each particle to a second measurement, which will be local. So it only will be restricted to that one particle. So each one of these particles. And then we'll ask ourselves our question. So kind of now we will advance our setting to the following. So we already considered that we prepared these three particles in the state psi, which is the state plus, plus, plus. Then they somehow, if we had our classical intuition, if it were our three pigeons, and it's kind of three pigeons because this state between all these three particles is not correlated. So somehow there are these two boxes, L and R, and they're somehow distributed over these boxes. And then what we do, we measure these three particles and we measure them in a state which we call phi, which is the state where each particle is in a state plus I, where plus I is this slightly rotated state. So it's 1 over square root of 2 L plus IR. And after measuring these three particles in such a state, we will ask ourselves a question. So in between our preparation and our measurement, these processes are also called, this procedure is also called a pre and post selection procedure. So we kind of pre-select on the state psi and post select on the state phi of these three particles. So this is just a bit of terminology which is used in research. So between these two steps, are three particles, is there an instance where two particles are found in the same box? And now we will actually show that for this preparation state psi and this post-selected state phi, actually none of two particles can be found in the same box. So there are no two particles which are in the same box, essentially. Which is in contrast to the classical intuition, which would say that, okay, if we have three particles, three pigeons separate from each other, aka in quantum language, the state is a tensor product, and then we put them in the boxes, and then we make sure that we kind of measure or look at this pigeon such that they're all three of them are still separate, which is now expressed by the fact that we post-select on the state where the systems are composed by a tensor product. So there is no any explicit correlation in the post-selected state. Then our classical intuition tells us, okay, like in between, there must have been two pigeons or two particles in the same box. But for quantum theory, this is not necessarily true. And again, it is crucial that neither the initial state nor the final state contain any correlation between particles. And also the preparation and post-selection are done independently. So maybe I'll just kind of note here that this is preparation, or it is also called pre-selection. And this is post-selection. Or we can also call it measurement, but usually it's called post-selection. And these are done independently.
Sorry.
Mm-hmm.
But I am missing in the part where, what if now that we know that we can't have two pigeons in the same hole, we measure every single hole and see how many pigeons they have?
Very good question. It also relates to the previous question, because these are two different questions that we can ask, right? So one question we can ask is purely about correlation. So the question of, are the pigeons in the same box or are in a different box, is about the relationship between pigeons. But the question about, like, let us ask a direct question: is this pigeon in the left box? Is this pigeon in the right box? And so is the second pigeon in the left box, or is it in the right box? Is the third pigeon in the left box or the right box? This is a completely different question, which which kind of reveals something about the connection of a particular pigeon to a particular box. And while with classical intuition, these two sets of questions kind of should bring us similar answers, probabilistically as well. In quantum theory, actually, we see that these questions give us sort of different answers. Like, for example, if you take this setting and then you ask a question, oh, are any two pigeons in the same box? You will get the answer no. However, if you start just measuring each pigeon individually, you'll start getting probabilistic answers, as in, oh, like the pigeon is in the left box with probability 1/2, in the right box with probability 1/2, and so on. So essentially they're gonna be an instance where, for example, with probability 1/4 or so, I think it's 1/4, where you would say that, okay, I found the first pigeon in the left box, I found the second pigeon in the left box, and I found the third pigeon in the right box. But still, this is a question you asked. Your state, which is a quantum state, is already disturbed by this question. And so you cannot ask up to this. Of course, if you ask a question, oh, are pigeons 1 and 2 in the same box? You will get the answer yes, because they're kind of, you collapse them both into being in the left box. But if you don't ask the question about their particular position in relation to the box, but just ask the question, oh, are you in the same box? Like skipping the part with obtaining their exact position, then you'll get the answer no.
Okay, but then if I ask a question, are the pigeons 1 and 2 in the same box? I will get no. Then I disturb my measurement, and when I ask, are pigeons 2 and 3 in the same box? The probability is going to be 1/4. Because at least 2 pigeons have to be in the same box. So the first one I ask is always going to be no, but then the other set of questions, at some point it has to be yes.
I mean, so the first time you ask, your answer is going to be no, and your final state is going to be like the state you post-selected on, right? Mm-hmm. And then then you can ask whatever question you want, but then you should also, and then it also depends on which state you're going to post-select after that.
I see.
So okay. This operation is highly dependent on which state you prepare the pigeons in and which state you post-select the pigeons in. Like, for example, if you choose some other state, not this phi state, then you will get some non-zero probability, or you might get some non-zero probability of the pigeons being in the same box.
Okay, and when you say post-selection, mm-hmm. It's really just what we got as a measurement, right? We cannot influence it. We cannot choose which output we're gonna get.
So essentially, the idea here is that, so you just measure in the basis which has this state. So essentially you measure in the basis which has the states phi, and the state which is orthogonal to it, right? Mm-hmm. Which completes the basis, right? Mm-hmm. And then kind of you run the experiment and then you only consider the case.
Okay. Yeah.
Gets that outcome.
Okay. Thank you very much.
Yeah, you're welcome. Thanks for the questions. Okay, so given the result of this final measurement of the state we post-select in. So then we can, so suppose that first at intermediate time, we indeed find the particles in the same box. Then the state would collapse to the state which we label as psi prime, which is just applying our projector to the state psi. And this is up to normalization, so I won't kind of linger on that, but essentially it just collapses the state of the first and the second particle into the superposition, equal superposition of being both in a left box or both in a right box, and the third particle is still in a plus state. However, this state is actually orthogonal to the state on which we post-select. So psi prime, scalar product with the state phi on which we post-select is 0. So yeah, this is easily seen if we consider first the scalar product of plus I and L, which is 1 over square root of 2. Then this the scalar product of plus I and R, which is minus I over square root of 2. Yes, and then we just need to calculate the scalar product, which is plus I on the systems 1 and 2, which come from the final state. And then the state we have collapsed to, which is LL on 1, 2 plus RR on 1, 2, which gives us, so the first term is just like the scalar product of plus I and L squared. So we get just 1 over square root of 2 squared. And the second is the scalar product of plus I and R squared, which gives us this. And because we chose this phase here so conveniently as I, and I squared gives us minus 1. Here we get 1 minus 1/2 minus 1/2, 0. So yeah, this was just a quick justification of the fact that these two are orthogonal. And so essentially what this means is that, like, if we have a post-selection on the state phi, and we're checking if these two particles, pigeons, are in the same box, then we essentially need to calculate this probability up to normalization, but we get this 0 anyway. So this means that essentially our initial assumption that we assumed that we found the particles 1 and 2 in the same box was incorrect, which means that 1 and 2 are not in the same box. And as I mentioned already in the beginning, because all procedures are invariant under permutation between any two particles, so it can also be for particles, so the same procedure can be calculation can be done for the particles 2 and 3 and the particles 1 and 3 as well. We see that the same statement can be made for particles 2 and 3 and also for particles 1 and 3, which essentially means that there are no two particles which can be found in the same box. Okay. So this is in a direct violation of our classical intuition, or this classical pigeonhole principle, where we would have two particles in three boxes, and there would be two particles which would be in the same box, but here no two particles can be found in the same box. This principle can be generalized for n particles and m boxes. So if we have n particles and m boxes, m is less than n. So the usual Dirichlet principle would say that there is a box which contains at least n minus m plus 1 particle. But in quantum case, we actually can again guarantee that there is such a pre and post selection procedure of such that no two particles are in the same box. Independent of what is the exact values of n and m. And the states in which we have to prepare the particles are the following. So here the states are k. So J is the label of the particle, and the state k means that the particle is in the kth box. And there are m boxes, so here the particle is uniformly superposed over all m boxes. And we have to prepare each of n particles in such a state. So kind of the state psi on which we pre-select is the 0, 1, so on, 0, n. So this is pre-selected state. And the state on which we post-select each particle is in a state that's called eta. Which is kind of a Fourier transform over states over the states of being in the first box and so on in the mth box. And the state on which we post-select is then just combined state of all these particles. So I will not do this derivation in class, but this is part of the exercise. So here you just need again to use to see what exactly sorry, I mixed up the superscript and the subscript. So here you need to see what is exactly this projector, and then you just need to show that actually psi this projector phi is equal 0. So this is fairly straightforward. Okay, so now again to recap and to give some insights and what exactly we can note from this thought experiment. So first thing that we can note is something that I already mentioned. So neither the state we post select on nor the state we pre-select on are correlated. But because we are asking questions about whether the particles are correlated or not, and our projectors are correlated, after asking this question of kind of making this measurement, the particles become correlated. So this also means that kind of this entanglement resource is found not in the preparation or post-selection in a particular state, but is found in the particular question that we ask. So kind of this entanglement is between particles is generated by the measurement rather than by preparing the state in an entangled way. Also, something that was already questioned is, so if we measure each particle individually, they will appear uncorrelated. So suppose that, again, we're not asking the question about whether they're in the same box or different box, but we're asking, is particle 1 in the box L? And then if we ask this question for each particle, we just make their measurements on one particular system. And of course, there are going to be no correlation revealed whatsoever. And this is kind of a fundamental difference between which kind of questions we can ask, or which kind of so which kind of measurements we can make. And this you can see it also as a trade-off between knowledge we can have about correlations or knowledge we can have about direct positions. And this is very, very much in relation, or kind of in this fundamental relation with the uncertainty principle. So one way we can state the uncertainty principle is actually to say that, so we have some knowledge about the system, but actually we can only have half of the all possible knowledge about the system. So suppose that if we characterize the system as the points and momentum position space, then according to the uncertainty principle, or this interpretation of it with using knowledge, we can say, we can only know its exact momentum, but then I don't know anything about its position, or we can know its exact position, but I don't know anything about the momentum. And this is kind of similar to saying, if the system is in some position, has some exact position and exact momentum, I can only know one of them. The other one I cannot know because of the uncertainty principle. So in a sense, I can only have half of the knowledge about the system. And here it's the same. So we can either ask a question about, how are the particles correlated, and have knowledge about that, but have absolutely no knowledge about where exactly the particles are. Or we can choose another set of questions saying that I want to know where exactly the particles are, but then I don't gain any information about their correlation, or how their states are correlated. So essentially, if we measure each particle individually, they're going to be like 4 options, each with equal probability. Like the first, they're both in a left box, they're both in the right box, one is in the left, one in the right, and one in the right, and the other one is in the left. Yeah, and so this I mentioned. Yeah.
Quite get what you said about this correlation. Like, do you mean like they're in a certain state and then we measure the correlation? Because like, as I'm thinking of it now, like if you measure the position of the particles, then somehow you also find the correlation between that or not.
You actually don't, because like, so remember, all these measurement results are probabilistic. So in 1/4 of the cases, you'll find they're both in left box. In 1/4 of the cases, you find they're both in the right box. In another fourth, you find that one in the left and one is in the right. And in another fourth, one is in the right and another one is in the left. That kind of distribution doesn't solely tell you anything about correlation, in a sense.
Yeah, I guess I have to think about it.
Yeah, just like give it some thoughts. So that there is some kind of, like in quantum theory, there is this sort of trade-off between knowledge about correlations and knowledge about kind of exact position of something.
Yeah, and these are like conjugate, so to say.
Yeah.
Yeah, related with a Fourier transform. Okay.
And so the final,
sorry, if you go ahead.
Yeah, it's just one remark, and then please ask away. So the last remark I wanted to make is that actually, if we ask about correlations, these are global measurements, so we have to make a measurement on the whole system, or like part, like on this first and the second particle and so on. In some cases, they might be better than asking about positions directly, because then the detail measurement introduces disturbance, or can introduce disturbance, and these kind of questions, or are particles in the same state, in the same box or not, might minimize disturbance. Of course, like, it does not apply exactly to this case, but for example, if you have particles in a state LL plus RR, and then you ask a question of, are you in the same box or in a different box? This actually does not disturb state in any way. And then you get the answer that they are both in the same box. And then, for example, if you start asking the question directly and measuring each particle individually, this would collapse the state either in LL or RR. Which is, of course, bad. We don't want to disturb our state, because we don't like to prepare states too often. But this is just a side remark of how these correlation questions might be, in some cases, better than asking directly. Okay, I think this is everything I wanted to say for today, so please shoot with the questions.